Hello, my name is Naje George, and I will be presenting to you propagation of Ab-Initio quantum dynamics. I'm working on this project with my primary advisor, Dr. Philip Furre, and my co-advisor from San Diego State, Jose Castillo. So to give some background, we are going to be looking at the time-dependent electronic Schrodinger equation, and this equation really is the basis for a lot of the research that my lab group does. We are basically taking a Hamiltonian and applying it to a wave function to get future states of that wave function. Um, with breaking this down and reducing the dimensionality of this equation, which uh, tends to be very high in dimensions, we can basically express this computationally as a unitary propagator acting on a vector to get future states of that vector, which will produce the wave function over time. So the algorithm that we're using is totally fewest switches surface hopping, and the reason why we're doing that is because this algorithm allows us to reduce computational costs pretty significantly by letting us only focus on the electronic uh, part of the Schrodinger equation. The main feature of this is surface hopping, which is the act of switching from one potential energy surface to another. When we do this, for my project, it tends to be jumping from the excited state, the first excited state to the ground state. So you can imagine that there's a lot of kinetic energy in the excited state that gets reduced once hits the ground state. So we need to be able to rescale those velocities, which will affect the momenta and the kinetic energy. And we do this along the direction of the non-adiabatic coupling vector. So looking closer at the surface hopping, for our algorithm, we are using leapfrog Verlet, second order algorithm, to be able to update our velocities and our positions. Velocities at the half step, positions at the integers time step. However, for the surface hop in turbo mode, the current algorithm does a first order half step um, propagation in order to get the exact second or the exact integer time step velocity to rescale. However, for my modification, I am still performing leapfrog during the surface hop, but I'm taking the average of the new half step and the old velocity half step in order to get an average of the velocity integer time step and then rescaling that to use in our algorithm. And then from there, the rest of the simulation will use the new velocities and kinetic energies. So for my project, or for this presentation, I gave the example from aluminium, which is a carbon, nitrogen, and four hydrogens. Um, my simulations I run basically 50 trajectories in a simulation suite with a basis set, a DEF2 SVP, which is basically our test basis set. Um, and I use a time step of 0.2 femtoseconds with a total time period of 200 femtoseconds. And I got this based off of based off of other computational papers. So for the current algorithm, we can see that there's a notable decrease in energy beyond chemical accuracy. If you look closely, there's a gap of basically 2.2 times 10 to the negative 3 Hartree, which is greater than a chemical accuracy of 1.6 times 10 to the negative 3 Hartree. However, when we apply our modified algorithm, we can see that that gap lessens. So we're looking at a gap of around 7 times 10 to the negative 4 Hartree, which is significantly less than chemical accuracy, which is what we want. And if we compare this on the same graph, we can see this decrease, we can see this decrease in the energy gap further. We can see that our modified algorithm conserves energy a lot better than what we have currently in TurboMol. So if you want to look, I do this more of this. I look at other observables such as excited state lifetimes and product distribution, and I also look at other molecules such as titanium tetraoxide tetrahydroxide, excuse me. So if you want to see more about, all the different facets of how I compare these algorithms, I would love to see you at my poster. Thank you very much.